everyone. So now let's pick up from where we left off and talk just briefly about crystallography and see if we can make some sense of the relationship between that and Euclidean symmetries. So as I mentioned at the very beginning, crystals are objects whose underlying atoms or molecules are organized in a lattice structure. And we're going to say that two of these crystals are equivalent if there's a symmetry, a Euclidean symmetry that transforms one into another. And there are 230 different possible subgroups of E3 which carry a lattice into another lattice, and those are the 230 different types of crystals. But those are very complicated, and we're not going to look at those. Instead, we're going to look at crystals in two dimensions. These are sometimes called plane groups or wallpaper groups, and it's probably best to start out by looking at an example to see what I mean by a wallpaper group. So the artist M.C. Escher specialized in using different kinds of symmetry to produce his art. And this image is taken from a book, Fantasy and Symmetry by Carolyn McGillivray, published by Abrams in New York City in 1976, which contains a mathematical analysis of a bunch of Escher's pictures, along with samples of pictures. This is just a small piece of one of those pictures. And what I've drawn on the picture is this lattice work of green lines. And that, the point of that lattice is that the picture of the birds and the fish, there's black fish and white birds here, is symmetric under translations in the lattice. For example, if I take this square here, and I shift it this way by 1 unit, this bird goes to that bird, this bird goes to that bird, this fish goes to this fish, that fish goes to that fish, and similarly for all the other birds and fishes. So this image has a translation symmetry 1 unit to the right and also 1 unit up. And also any combination of those. Namely, no matter how many, if you imagine this going on to infinity, which of course it doesn't, then you could shift any number of units to the right or to the left and any number of units up or down, and you would get the same picture. And so we say that this image is invariant under the action of a lattice, or it's periodic with respect to that lattice. Namely, it's made up of blocks, and each time you take an element of the lattice and shift that block around, the picture comes back to where it was before. Here's another example. This picture was taken from a website about plane symmetry, and there's the link. It's at the University of York in the United Kingdom. And this picture also has a lattice symmetry in it. Here I've drawn some of the cells of the lattice in green. You notice that they're rectangular cells because if you shift kind of only 1 unit, say from here to here, it doesn't, the image doesn't match up because the commas are in, I think of these as commas, maybe they're apostrophes, I don't know. They don't line up. You have to shift by 2. So if you shift from here to here, then this image repeats. And if you shift from here to here, this image repeats. So this is another example of a pattern which has translational symmetry by a lattice. So we're interested in understanding patterns which have translational symmetry and maybe additional symmetry beyond that. And we're going to study groups which have the property that they have a lattice in them, and also maybe some other symmetries, and they're subgroups of the Euclidean group. So remember that the Euclidean group, or the plane group, consists of pairs, big A, little a, where big A is an orthogonal 2x2 matrix. So it's either a rotation or a reflection. And little a is a vector. And the action of these symmetries, if you have a symmetry AA and you apply it to a vector xy, what you do is you multiply the vector xy by a, and then you shift it by the little vector a, little a. So it's a mixture of rotations and reflections and translations. And this group has a subgroup consisting of translations. Those are all the elements where the matrix is the identity. And then if the matrix here A is the identity, this just shifts the vector by A. And there's also a surjective homomorphism where you forget about the translation and just look at the A, and that's an orthogonal matrix, and the kernel of that homomorphism are the translations. They are the things that are going to the identity. And remember, this group isn't abelian. If you take AA and you multiply it times BB, you multiply A and B together, but A acts on the translation B, and so they're mixed up. And we're going to be interested in subgroups of this group, and if you have a subgroup H in E of 2, it's going to have the same structure. Namely, you can take its intersection with the translation group, and you can also take the image. If we call this map pi, for example, you can take pi of H, and that's going to be inside O of 2. And these two the subgroup of translations that actually belong to H is called the translation subgroup of H. And this group, which is not a subgroup of E of 2, but rather a subgroup of the orthogonal group, is called the space group, or sometimes the point group of H. And it's a subgroup of the group of rotations and reflections. And we're interested in groups where the translation group is our lattice. So if our shape is symmetric under this subgroup H, then on the first place, it has to be preserved by the action of this lattice. And then maybe there's also some additional H's that come from the space group, which give other permutations of the lattice which preserve it. So the definition of that is a wallpaper group, or a plane group, is a subgroup of the Euclidean motions where the translations are a lattice and the space group is finite. That's the definition we're going to use. And if you go back to our Escher picture, what is the symmetry group of this? Well, we already mentioned that we have the two symmetries. Maybe I'll call them A, which is shift one right, and B, which is shift one up. But those aren't the only symmetries. So then you can do A a bunch of times and B a bunch of times. And N and M can be integers. They could be negative, meaning shift to the left or down. So these are all the shifts. But there's another symmetry, because if you look at this little red dot here, if you take this picture and you rotate it by 180 degrees, this bird, which is flying down and is over here, gets rotated around to this bird, which is flying up. And this bird, which is flying up, gets rotated to this bird, which is flying down. And then over here, this bird, which is flying down, becomes this bird here, which is flying up. And this bird, which is flying up, becomes this bird, which is flying down. And the fish, which are in the gaps here, they also follow this pattern. And if we call this, you can't see them, but if you were to take this fish over here, and you do this rotation, where does it go? Well, this fish here is going to go all the way over to here, and this bird. And so it's going to become this bird, which is flying up. So the entire diagram can be rotated 180 degrees, and it will give you the same picture. So if you were hanging it on your wall and you rotated it around this point, you'd get the same wallpaper pattern. So that symmetry, let's call it R. And it's the rotation around this point here. And we know that if you do it twice, you get the identity. How does it interact with A and B? Well, for that, we can do a little bit of a calculation, maybe in coordinates. So A takes a vector xy to x plus 1y. A inverse takes a vector xy to x minus 1y. B takes a vector xy to xy plus 1. B inverse takes a vector xy to xy minus 1. And what does R do? Well, R takes a vector xy and it just negates both coordinates, right? It takes this point here, which is 1, 0, and takes it all the way over to here, which is minus 1, 0. And it takes this point here, which is 0, 1, and takes it all the way around to this point here, which is minus 1, 0, minus 1. So if we compute RA inverse of xy, we get R x minus 1y, which is 1 minus x minus y. And if we compute AR xy, we get minus x minus y a, which is 1 minus x minus y. And those are equal. So we have the relation RA inverse equals AR. And the same calculation will show you that RB inverse equals BR. So in a sense, we have a kind of a version of the dihedral group, except that we have the lattice of translations, and then we have one rotation which has order 2 and passes through the A's and B's but inverts them. So an arbitrary element of the group is either in the lattice, it's either of the form A to the M, B to the M, or it has an R in it. And any element that has some mixture of R's and A's and B's can be rewritten in this form using these relations to move the R all the way to the left, messing up the A's and B's in the middle. So you get a bunch of R's, then a bunch of A's, then a bunch of B's, because A and B commute with one another. I should have maybe mentioned that. And then, since R squared is the identity, there's either no R's or 1 R's. So this is the symmetry group of this Escher picture. What about the commas? Well, again, we have the lattice. So, but maybe I should just to hammer this home. The translation group subgroup in this situation is the AB group, and the space group is of order 2, or the point group, which is what happens if you look at the image in the orthogonal group, forgetting about all the translations. So it's just generated by R with R squared equal to the identity. So the point group here is Z mod 2. What about the commas or the apostrophes or whatever they are? So the commas similarly have a shift. They have the A shift, shift left, right. And they have the B shift, which is up, down. Now, in this case, the A shift there are different lengths. The A shift means you go all the way from here to here, whereas the B shift, this is the A shift, this is the B shift. So here's A, here's B. Because you have to shift sort of 2 commas over in order to get it to match up again. But then you have another symmetry. You can reflect this whole picture around this axis, let's say. And let's call that M. So in terms of the coordinates, A increases x by 1. B increases y by 1. Here, just to be clear, I'm using coordinates where this, even though it looks like it's 2, is only of length 1, because I want to use the lattice coordinates. I want a 1 shift to carry the picture to itself. And then there's M. What does M do? M takes xy. It doesn't affect y. Oh, and maybe just to be clear, A and B commute. M just reverses the x coordinate and leaves the y coordinate alone. But it doesn't send x, well, we could use x goes to minus x, but the way I've drawn it here, if this is 0 and this is 1, then this mirror takes 1 to 0 and 0 to 1, so it's actually 1 minus x. And now let's just notice that M commutes with B. mbxy is mxy plus 1, but m doesn't do anything to y. And bmxy, sorry, this is 1 minus x, y plus 1. This is 1 minus x y b, which is 1 minus x y plus 1. And these are equal. So mb is bm. But on the other hand, if you do ma inverse, this is times xy. This is xm. This is, so m a inverse xy is m x minus 1 y. And this is 1 minus x minus 1 y, which is 2 minus x y. And am xy is a times 1 minus xy, which is 2 minus xy. And those are equal. So m has this dihedral property, but only for one of the basis elements, not the other. And again, the elements of the group are of the form a to the n, b to the m, or m a to the n, b to the m. And m squared is the identity. So again, the point group is Z2, and the translation group is generated by A and B, but it's still a different symmetry. So it has the same point group and the same translation group as the previous example, but it's a different group because of the way the point group acts is a little bit differently. It's reflections instead of 180-degree rotations. So as I mentioned, there are 17 altogether, 17 different ways to do this, to make a lattice. And this picture, which I took from an article by Doris Schatzschneider in the American Mathematical Monthly called The Plane Symmetry Groups, Their Recognition and Notation, tells you how to make all of them. And the only thing you need to know is how to read these diagrams. And so let's start with this. Let me just sort of give you a clue as to how to read this diagram. So let's, each row, the two diagrams are the same. They're just slightly different information. Let's take this picture right here. What does this picture say? It says the plane group, it draws a lattice. It has this line with a dot here, a dot here, a dot here, and then this region is shaded. What are we supposed to make of all of this? Well, the parallelogram is a cell of the lattice. So if you wanted to draw the lattice, you would keep going like this, and then like this, and then like that. The dots tell you about the symmetry, the extra symmetries. So in this case, the dots are diamonds. And if you look down below, the diamonds say these are centers of two-fold rotation. In other words, what that's saying is that there's an additional symmetry that's obtained by rotating this picture 180 degrees around that circle. So if you were to do that, then if I were to, let's say, draw an arrow here, just so we can keep track of orientation, when I rotate this around 180 degrees, this parallelogram here comes over to here, but the arrow ends up pointing in a different direction. And you notice that there's also little diamonds here and here, which means there's also rotational symmetry there. So if I go like this isn't the best picture of the lattice. Then if I rotate this picture to here by 180 degrees, then this shaded region comes to here, and the arrow points down, and this arrow here points up. And there's also a 180-degree rotation possible around here, which is going to make this arrow here go up, and this arrow here go down. So this is the corresponding shaded region after 180-degree rotation. And if you keep this up, you get a picture which looks like this, if I've done this correctly. And so this is a picture of a lattice which has an additional 180-degree rotation symmetry. And it's the lattice that we saw in the Escher picture. Because if you go back to the Escher picture, don't worry so much about the shape of the squares, but remember this lattice, it has a rotational, 180-degree rotational symmetry about this central point here. But it also has, I could also have rotated it around this point. If I rotate it around this point, this bird rotates to this bird bird rotates to that bird, and so on. And there's also a rotational symmetry around this middle point, which would take this bird around to here. And those are the additional symmetries which are marked in this picture. And the shaded region, the significance of the shaded region is that if you, once you've filled in something into the shaded region, then if it's going to remain symmetric, everything else is determined. So for instance, here, if I put this arrow here facing this way, because of this rotational symmetry, I have to get an arrow which faces the other way. So if I were going to try to make a pattern with this symmetry, I could put anything I want in the shaded region, which is half of a cell in the lattice, and everything else would be determined. And in fact, in the Escher picture, the half of the cell, there's different ways to draw the half, but if you look here, basically what you've got on this side of the cell is the same as what you've got on that side of the cell, but it has to respect this 180-degree rotation. And the other picture that Schatzschneider gives you is a slightly different way of dividing it up, where instead of dividing it vertically, you take a diagonal, but it produces the same picture in the end. So from this little diagram, you could reconstruct that Escher fish and bird picture. This one gives the commas. And I'll just indicate that very briefly, because if you take, again, you draw the cell, so its cells look like this, and it has now two mirror lines. And so what it's telling, and this region here, the mirror line bisects the cells like this. And this is the shaded region. And what this is saying, I guess I have to decide what is a cell here. Let's draw just this much. There we go. So here's our cell. Here's two cells. Here's our mirror line here and a mirror line here. And this is the shaded region. So because of the mirror, whatever I put here, let's say one of those commas, so if I put an arrow that goes like this, I have to put an arrow here that goes like this. And there's also a translation. I can move this cell down here. So I would have to put an arrow here which goes like this and an arrow here which goes like this. And again, there's mirrors here and here. So you get this picture where there's a kind of mirror symmetry with half the period of the shift symmetry, which is what we saw in the commas. So this is the commas, and this is the fish and the birds. And every one of these gives a different pattern, which you can try to find in the paintings of M.C. Escher. Let's do one more, because there's one type of symmetry we haven't talked about, which is called glide reflections. So this is the case PG. And I've copied the little picture here, but I turned it on its side so that it kind of matches this Escher picture. These are the happy guys and the unhappy guys. So the basic cell is the unit of translational symmetry. That's this big red rectangle. And if you move the big red rectangle, let's say from here to here, then this guy here is going to move to this guy, and this unhappy guy here is going to move to that unhappy guy, and so on. So that, and similarly, this happy guy is going to move to that happy guy. But this and this, there's no translational symmetry here and here, because if you just move this up to here, then this happy guy is in the wrong place. Instead, the symmetry that you have is called a glide reflection. And what happens there is that this lower unit moves up and flips, so that this happy guy moves up to here and then is reflected around the origin. And this is a symmetry of order 2. If you do this twice, you get a translation, because the first time you do it, the happy guy here goes to the happy guy here, and the second time you do it, the happy guy here goes to this happy guy here who's kind of cut off. So this is a symmetry of this picture whose square is a translation. So again, the point group is of order 2, but now instead of having an element in the group whose order is 2, you have an element of infinite order, because if you keep doing this glide reflection, you're going to sort of zigzag your way up the picture. And then, of course, you also have just the translation this way. And so that's what this dashed line means in the Schacht-Schneider diagrams. It means that this half of the cell moves upward and flips. So once you fill in the lower cell, once you fill this in here, this cell here is determined because it's the mirror image of this one. And I won't write out the group law for this, and that's an interesting exercise. But this is the one other. So there's mirror, glide reflections, and rotations, and those can be mixed together in very complicated ways to produce the 17 different types of symmetry.